So the question goes as, consider a two-way set associative cache with 250 blocks and uses LRU replacement. Initially the cache is empty. Conflict misses are those misses which occur due to the contention of multiple blocks for the same cache set. Compulsory misses occur due to the first time accesses to the block. The following sequence of accesses to the memory blocks is given and it is repeated 10 times. So the number of conflict misses experienced by the cache is. Now you have to remember in such questions that in respect to set associative cache, when we have to find out where each block will be present, so you have to find block number modulo total number of sets that are present here. Since it is a two-way set associative cache, so each cache line will keep two blocks. All right, so there would be total of 256 divided by 2, that is 128 sets, and each block will be present in block number modulo 128 set number. All right, now there are two terms that are given in this question. One is conflict misses and the other is compulsory misses. Conflict misses are the ones that will occur when a particular block has been brought to the memory before, but since it is replaced by using LRU replacement algorithm, it is now not present in the memory. And compulsory misses will occur when the first time the block is used and it has never been brought into the memory. All right, so first and foremost we'll find out the number of sets that would be present would be 256, that is the number of blocks, divided by 2, which would be 128. Each block will be present in what set number? Present in the given set number, and that set number would be given by the block number itself modulo the total sets, total number of set. All right, so if we have to access 128, it would be 128 modulo 128, which is 0. So it would come out to be in set 0. Similarly, 0 would be 0 modulo 128. It would again come out to be in set 0. Now, since we are given different blocks, I'll draw a table so that you will understand what happens when each of this block is accessed. Initially, we are only considering some entries that are given, like if I say out of this, I'm only considering these entries for the time being, and why I'm doing so, the reason will become quite clear soon. Initially, when block number 0 is accessed, it is a compulsory miss because it has not been brought into the memory before this. So it is a compulsory miss and the content of set 0 would be 0 only after 0 has been brought into the memory. Why I'm writing set 0? Because these are all those blocks whose block number modulo 128 would result in the value 0, and all of these blocks will be contender for set 0 itself. All right, now when 128 has to be brought, it is again a compulsory miss because 128 was not present, and since 128 was not present, it has to be brought in. Now you have to remember, since it is a two-way set associative cache, it means that only 2 blocks will be present per cache line. So now when the next block, that is 256, which will again cause compulsory miss, it will be brought in, one of them has to be replaced. And which one would be replaced? The one which was least recently used. Least recently used is 0. So the contents would become 256 like this. Next comes 128. 128 is present already in the set, so it is a hit, but the order changes because now the least recently used is 256. Then comes 0 again, which is a conflict miss because 0 has been brought into the memory, but it is now not present because it was replaced. Alright, then comes 128, which is again a hit. It is present in the memory, but for least recently used purposes, we change the order. Then 256, again a conflict miss, and the set looks like this now. And for the last in this part, 128, which is a hit, and the order becomes this. Alright, this was for the first half, or some few block numbers that I have underlined here. Now for the remaining ones, you will notice that almost the same pattern is followed. That means when one is brought into the memory, 129, 257, all of them would contend for the set number 1, because block number, that is 129 modulo 128, would give you 1. Similarly for 1 and 257, when we do modulo with 128, it would give you 1. Alright, so the content of, or the way in which set 1 would look like, it would be similar in the manner that is represented here. Alright, this was the first iteration. Remember, there are 10 iterations in the same way that are done. This was the first iteration for almost the half of the entries, and for these half of the entries, you can see there are 2 conflict misses. Alright, 2 conflict misses, and you can calculate for the remaining half entries also, there would be 2 conflict misses. Remaining half entries also, there will be 2 conflict misses, and the total conflict misses come out to be 4 for the first iteration. Alright, now we have to check what the other iterations would look like. Similarly, we would do the same thing for other iterations for the same half. Alright, so if we write down here block number, hit or miss, and set to 0 content. Now one thing you have to keep in mind, this is the second iteration. Alright, in second iteration, the initial content would be the 256 and 128. The last content of the previous iteration would become the first content of the next iteration, which is the second iteration. So in case of second iteration, when initially we access 0, since 0 is not present, it would be a conflict miss. No compulsory misses would occur, because in the previous iteration, all these blocks 0, 128, 256 and 129 and 257 have been brought. So 0, again a conflict miss, and the set 0 becomes like 128 comma 0. Then comes 128, it is a hit, the contents become like 0 and 128. Then comes 256, 256 is a conflict miss. Alright, conflict miss, the contents are like this. Then comes 128, 128 is a hit, 256 and 128. Then comes 0, 0 is a conflict miss, the contents change again. After this 128, 128 is a hit, but the order changes. 256, conflict. Alright, it becomes like this. And the last one is 128. 128 is again a hit, and the order changes. Now if you notice carefully, the way in which the order or the values in set 0 are changing are almost the same as in the previous iteration. See, apart from the first entry 0, 128, 128, 256, 256, 128, 128, 0. So we can say that this iteration would be repeated after in remaining 8 iterations as well, because after we have done the first iteration, we would not see any compulsory misses, and after all the compulsory misses have been seen, this would be the pattern followed. This is the pattern for half the number. Alright, if you see in this case, total conflict misses here would be 4 plus 4, because 1, 2, 3 and 4, and for the remaining half 1, 129, 257, you will calculate, it would come out to be 4 again. So the total is 8 here. So the total number of conflict misses in 10 iterations would be, for the first iteration total was 4, for the next 9 iteration the total is 8. Alright, this gives you a total of 72 plus 4, which is 76. So you can fill in the blank here. The answer would come out to be 76. So this was all about this question. Basically you have to remember what are set associative cache and how different block numbers are calculated. Other information is given to you. You have to be a little quick in judging what pattern would be repeated, and you'll be good to go with this question. Thank you for is consider a computer system with 10 physical page frames. The system is provided with an access sequence which is given to you as A1, A2, A3 till A20, and again followed by A1, A2 and so on till A20, where each AI is a distinct virtual page number. So I have written this sequence here, A1 till A20, and again this will be followed by the sequence A1 to A20. So each of these A1 and A1 are the same page, but A1 is different from A2. That is what it is specified, that each AI is a distinct page number. The difference in the number of page faults between Lifo policy, that is last in first out, and optimal page replacement policy is. So this is what you have to find out in this question, that if we use last in first out policy and optimal page replacement policy, how different pages would be replaced in what manner, and what would be the difference in the page faults that would occur. Okay, so we'll start with the LIFO policy first. In LIFO policy, what concept is actually used is the page that entered the frame set at the last would be the first one to be removed or replaced. Okay, so last in, the page that was entered last is the one to be out the first. Okay, so if we have 10 physical page frames, let's make 10 page empty frames. 10 empty page frames. Alright, so these are 10 empty frames, and initially we have to put all these pages in them and service these requests one by one. At some point some replacements would be required, but since initially all these 10 frames are empty, we can safely put A1 to A10 into them one by one. Alright, and since none of these pages A1, A2, A3 till A10 is present in the memory, or these pages are not present in the frames, therefore each page will cause one page fault, because whenever a page is required and its content have to be executed but the page is not present into the memory, the page has to be brought into the memory for the first time, and this is what is known as a page fault. So all these pages, the first 10 pages cause 10 page faults. Alright, now we are done with the first 10 pages. Let's go to the 11th page. Since 11th page cannot be directly put without a page replacement, so we have to replace one of the pages that is initially present in the frame set. So what policy would be used for replacing for putting the 11th page? The page in this frame set that was put in the last will be replaced. So at the page, the 10th page was the last one to be put in this frame set, so it will be the first one to be moved out. So we'll remove A10 and replace it by A11. So the 10 page frames now have the pages A1 to A9 and A11, and since A1 was not initially present in this frame set, so this also causes one page fault. Similarly, now we have to put A12. A12 will again replace the page that entered this frame set at the last, or the last page to enter this frame set. The last page was A11. So when we have to assign A12 to one of the frames, what page would be replaced? A11 would be replaced. And similarly, A12 would cause one page fault because it was initially not present. And we'll continue in this manner. A12 will be replaced by A13, A13 by A14, A15 would replace A14. Now A16 replaces A15. Again, when A17 has to be put, this will replace A16, A18, A19 and A20. And why we are doing so? Because every time we have to put one page into the frame set, we will be replacing the last page that was put into this frame set. Now when we come to this page A1, since A1 is the same page that is present here, therefore we do not need to replace any other page to bring this A1 into the frame set because it is already present. Therefore, A1, A2, A3 and so on till A9, all these pages would not cause any page fault. Each of these pages caused 10 page faults because they were not initially present, but A1 to A9 would not cause any page fault because they are already present. Alright. So now coming to A10. A10 would replace the page that entered this frame set at the end. This A10 would now replace this A20 because out of all these pages A1 to A9 and A20 was the last one that was put in the frame set. We won't be considering these pages because they have not entered after A20. They were already present before A20. Okay. So now A10 would again replace A20 and A10 would be present. And similarly, A11 would replace A10, A12 would replace A11 and so on till we get the last page as A20 again. Okay, so in this way we would result into 11 more page faults. Why 11 and not 10? Because here the 10th page A10 was also brought into a memory at a time when it was not present. So this would also cause a page fault. Okay, then 11th page, then 12th page and so on till 20 page. So this is a total of 11 page faults, and 10 plus 10 plus 10 would give you a total of 31 page faults. So 31 page faults are occurring in the case of Lifo. Now let's calculate what are the number of page faults that would occur in the case of optimal page replacement. Now what is an optimal page replacement policy? Optimal page replacement policy basically looks into the future. It replaces the page that will be used the farthest in time. Okay, the page that will be required at the farthest time in future. Okay, so optimal page replacement. Now again we would start with a set of 10 free frames. Let's make these here. Again, starting with A1 to A10, these are not present in the memory. They are not present in the frame set. Therefore, they would be brought into the frame set and they would be put into these frames without any replacement because empty frames are present at this time. Alright, but since they are not initially present, they cause 10 page faults. One page fault for each page. Now, when we have to put A11 into one of the frames, we need to replace one page, and what replacement policy would we use? Optimal page replacement. Optimal page replacement says that see the future that means see to the right which pages would be required in the future and select that page that would be used at the farthest point of time in this sequence. So we have pages A1 to A10. If I start seeing to the right of A11, that is the future requirement of pages, I come to see A12, A13, 14 till A20, and then I see A1. Okay, A1 is present, but A2 is present at a, or A2 would be required at a farther time, more afterwards than A1, then A3, then A4, and I see that A10 is the page that would be required all after all these pages A1 and A9 would have been used, or their requirement would occur, the requirement of A1 to A9 would occur before A10. So this is the page that would be required farthest in future, and this is the page that I'll choose for replacement. So A10 would be replaced by A11. Again, when I have to put this A12, don't confuse it with these set of A11 and A12. We are first putting the first sequence only. Okay, so now I have to put page A12. I again see in the future or towards the right hand side of the sequence that is present to the right of A12, and I see that out of A1 to A9 and A11, A11 would be the page required at the farthest point of time. Okay, so I again replace A11 by A12, and continuing in this manner, A13 would replace A12, A14 would replace A13, and so on. A18, A19 and A20. Alright, now when we come back to A1, we see that this page is already present, so no page fault. Now each of these page that we just saw, A11, A12 till A20, would cause one page fault each because they were not initially present, so a total of 10 page faults. Now A1 to A9 is already present and A20 is present. So A1 to A9 would not cause any page fault because they are already present into the memory. Now coming to A10, again A10 would choose a page to be used farthest in future. This A10, now when we see to the right of A10, we have A11, A12, A13, A14 and so on till A20. So the requirement of A20 is there, but there is no requirement of A1, A2, A3 and so on. So we need A20 but we don't need A1. So we replace A1 here. After replacing A1, I put A10 here. Okay, I repeat this. We now have to put the page number A10. When I see in the future, I would need page number A20. Okay, I would never need A1, A2, A3 and A9 again. When I see from this point of time and I see towards the right, the only page that is present in the page frame set and that is also present in the future is A20. So I have to keep this page. I cannot replace this page. I can replace other pages. So I start with A1 because A1 was the last one, or A1 is a candidate for replacement. So I replace it with A10. This would cause a page fault because A10 is initially not present. Alright, again when I proceed here and I come to A11, A11 would replace A2 because A20 is required, and if I have to choose between A2 and A10 to replace, A2 is the one that was least or that entered before A10. Okay, so you don't have to be confused here about that why A11 is not replacing A10. A10 has just entered into a system, and we have a page, or we have certain set of pages that entered before A10. So we prefer to replace these pages. So I replace A2, I replace it with A11, then I'll replace A3 with A12, A4 with A13, A5 with A15, A6 with A16, A7 with A17, A8 with A18, and A9 with A19, each of them resulting into one page fault. So this would give me a total of 9 page faults. Okay, 9 page faults. Now when I come to A20, A20 is already present, so I do not, sorry, this would give me a total of 10 page faults. Okay, so when I come to A20, A20 is already present. We do not need to replace any other page, and there is no other page fault. So the total page fault here is 10. This 10 for this 10 plus this 10 plus this 10. This is 30. So the difference that would come out would be 1. Okay, so in this case, in such type of questions, you need to carefully understand what the question is asking, and you have to apply the concepts of all the page replacement algorithms and such scheduling algorithms also when in questions like that, when you have to compare any two things, because there are chances that you will get confused. All right, so be careful while calculating, while performing such replacements or schedulings if in such questions it is required. So that's all for today's lecture. If you understood the video, please like it and share it with your friends, and tell us in the comment section below how did you find the video. Please subscribe to our channel of Easy Engineering classes for more lectures on computer science and other lectures of preparation series of GATE, UGC NET and Bank IT Officer exams. Thank you.